All right, welcome back. 7.2, we're going to be talking about the normal curve, the normal distribution, which is something that maybe you've heard about before. We have briefly talked about the shape of that normal curve. And this is another type of continuous distribution. There's a great example I like to use to show a normal distribution. However, it is a discrete distribution. So it's going to be interesting to see how we can use sort of discrete ideas to estimate continuous probabilities. So the example I want to use is rolling 2 dice. Rolling 2 dice. Think about the sample space there, right? When we've created a sample space, we have done like the possible outcomes on the first die, the possible outcomes on the second die, and we've listed all of those possible outcomes, right? So, for example, let's say this is die 1 right here, and there's 1, 2, 3, 4, 5, and 6, and then we got die 2 going vertically here, and we could have 1, 2, 3, 4, 5, 6. And so all of these individual pairs in the middle we could fill out, right? We've done this before. That would be all of the possible outcomes. So how does this relate to what I'm talking about? Well, let's draw a distribution. So on the x-axis, we have our outcome, right? And what are the possible outcomes we can have? Can we, when rolling 2 dice, roll a 0 or roll a 1? No, but we can roll a 2, right? So that's a possible outcome. We could roll a 2. We could roll a 3, a 4, and so on, right? So let's just go ahead and fill that out. And the maximum we can roll would be a 12. Okay. Over here we have the probabilities. Now we know how many total outcomes are there. There's going to be 36 total outcomes, right? Okay, so interesting. How many outcomes can we make a 2 with? Well, the only possibility of making a 2 is a 1 on the first die and a 1 on the second die, right? So that's only one possibility. So essentially what we would have is like a 1 out of 36 probability. Okay? How many different ways can we make a 3? Well, we can make a 3 with a 1 on the first die and a 2 on the second die. Or we could have 2 on the first die and 1 on the second die. And so now we have 2 possibilities. And so that's going to be 2 out of 36. And that's supposed to say 2 out of 36 there. Okay, I'm not going to label all of those values. We can kind of see how this is going to work, right? How many possibilities can we do to make a 4? Well, there's the 1, 3. There's the 2, 2. And there's the 3, 1. Right? So there's 3 possibilities. And what we see here is that each time we get an extra possibility. Until I say, how many different ways can we make a 7? Well, that's technically still 1 more. But that's the max. Okay? 7 is the most likely outcome. Now when I go to 8, how many different ways can I make an 8? Well, I would need at least a 2, right? A 2, 6. That's a 6. Right? A 2, 6. Or a 6, 2. There's 2, right? Or I can do the 3, 5, 5, 3. There's 4. And then I can do a 4, 4. And so I end up with the 5 possibilities. So 1, 2, 3, 4, 5. And I've gone back down. And essentially that's what's going to happen here. Now as I get closer and closer to 12, which how many different ways can I make a 12? Only 6 and 6. There's only one possibility there, right? And so we have this thing that kind of creates what we would consider a normal looking curve, a normal distribution, okay? I understand that it's a discrete probability, but it's a kind of a good way to show that shape and how it is created in almost everything. So in almost every situation, we can use a normal distribution to sort of make estimates and find probabilities. So separate from this, the normal distribution is continuous. It's not these individual dots, okay? It's not the individual dots. It's one smooth curve. The idea is, so let's go with an example here. Here's a normal distribution. Normal distribution, and this is the standardized normal distribution. It has a mean of 0 and a standard deviation of 1, okay? And what we get is just the standard curve. That standard bell-shaped curve, okay? That normal-looking curve. The idea here is if right in the middle is the mean, the average, right? And we've seen how this can create those sort of sections that we've talked about with probabilities and whatnot, where you can add the standard deviation, subtract the standard deviation, and so on. So this, very similar to our uniform distribution, the area under the curve represents the probability. Okay, and these individual like vertical lines that I draw here, those are like individual points. However, if we're talking about a normal distribution where the average is 0 and the standard deviation is 1, what's the probability that x is exactly 0.5? Well, because this is a continuous distribution still, that probability again is 0. Okay? So we have to talk about ranges. So we can talk about, well, what's the probability that we're between 0 and 0.5? And then we can be finding these areas. And this concept is actually even used in calculus, the concept of using rectangles to estimate area under a curve, right? Because if I pick two values here, let's say I pick this number here, let's call it 0.5, and then I pick this number here, let's say it's 1. Well, I'm trying to find this area essentially, right? But we know that this shape is not a rectangle. I can't just do length times width because of the curve, right? So in calculus, what they do is they take rectangles and they try to estimate the area under the curve, right? I can kind of draw a bunch of rectangles to kind of show what that curve might look like if I sort of break it into little rectangular pieces. This looks pretty good. If I drew this differently and I said, okay, well, maybe I don't want to draw as many rectangles, and I just draw one big rectangle and another rectangle and say, yeah, that looks like a normal distribution. Sure, not as good though. So the idea here is the more and more rectangles we make, the more and more times we break this up, the closer and closer we get to the actual area under this curve. The great thing about this, though, is our calculator is going to be able to do all of this calculation for the area under this curve for us. Just like we used with binomial distributions, Poisson distributions, geometric distributions, we have the calculator where we can kind of input values and figure out the area between two values. We're not going to find individual probabilities because those are all zero. So this is, in essence, one of the most important parts of statistics is the normal curve and being able to use this normal curve. Okay, this is the one I just said, the x equals 0, the mean equals 0, standard deviation 1. That's our standard normal distribution. It's kind of the way the calculator will default the options to. But the great thing is that we can make this centered around anything, spread around any standard deviation. So I could say that there's a normal distribution, just like last unit or last section, we do have to know what type of distribution it is. So there's a normal distribution with mean, let's say 42, and standard deviation 6. Okay, well, what will that look like? I'll just kind of sketch a curve. It means that the mean 42 is right in the middle, and it's kind of giving us an idea that as we move out from the mean in both directions, we're adding and subtracting 6. Okay, so this would be like 36, this would be 30, this would be 24. Okay, and this would continue, but the probability of that is getting so small. Because if I tell you that the average of something is 42 and there's a standard deviation of 6, and I ask you to calculate what's the probability that a value is between 0 and 5. Well, if the average is 42, the probability that I randomly select a number and it's between 0 and 5 is going to essentially be 0, right? So as we keep going to this, it flattens out and is eventually 0. So how about if I say, what's the probability that we're between, let's pick this 36, and then let's pick this value over here. So this would be add 6 again, right? So like 54 maybe. So we want to find this area. This is a pretty big area. Let's see what this probability is. So this is between 36 and 54, right? We can see visually that this should be a pretty big number, probabilistically, right? And that kind of makes sense, because if I tell you the average is 42 and pick a random number and you get to choose, well, I think it's going to be between 36 and 54, yeah, your chances are pretty high, right? So let's see what we do with the calculator. We're going to go to the distribution. So we're going to press second vars, and it's the first one that comes up and the second one that comes up. So there's normal PDF and normal CDF. Because we are dealing with continuous functions here, we're going to do normal CDF. And, oh, that should, sorry. And we get this screen. Lower, upper, mu, sigma, and paste. What this is saying is it's essentially talking about this area we've defined. So we're looking for this area. What's the lower bound of this area? This is technically the lower bound of the area. This is the upper bound of the area. The average is mu, right? I was using x bar, I should have been using mu. So the mu is 42, and then we have our standard deviation of 6. So going back to the calculator, lower bound, 36. Our upper bound is 54. Our average is 42. And our standard deviation is 6. So what's the probability? We get about 81.9%. So yes, pretty high probability there. Okay, and that is essentially how we figure out the normal distribution. Okay, so that's finding probabilities under the curve. So let's do one more. Normal distribution. Let's say we have a average of 38.7 and a standard deviation of 2.3. Okay. Well, I want you to find the probability that x is between, let's say, 39 and 41. Okay, it's a small little area. Oh, forgot my less than sign. It's a smaller area, right? It's a smaller standard deviation. Let's see what this probability is. So go ahead and try it first, and then see if you agree with what I got. So I'm going to go to second distribution, normal CDF, and the lower bound's 39, upper's 41, the average here is 38.7, and the standard deviation is 2.3. And so that probability ends up being about 28.9%. Okay? That's how we use the normal distribution and the normal curve. Okay? I think I'm going to stop it there. So that's finding area. Next time we'll talk about finding values. So the last thing I just want to point out is keep in mind that important concept that the area is equal to the probability, okay? And the values are all these little points down here, right? These are all the values we're talking about. Okay, so this would be a value, this would be a value, and so on. Okay? We'll get more into the reverse of what we're doing here next time. All right? I will see you guys later.